Welcome to What Happens When a Molecule Absorbs Light. So we've already talked a little bit about how light works, how photons are absorbed and things like that. But now let's discuss what happens to the molecule when it absorbs light. So when a photon is absorbed by a molecule, the molecule gains the photon's energy. The molecule has entered now an excited state. It may already have existed in an excited state, but most molecules exist in the ground state. So when it absorbs the energy, it's now been promoted up to an excited state. So when a photon is emitted by a molecule, the molecule then loses the same amount of energy that the photon then carries away. So for example, let's examine the ground state structure of formaldehyde, which is methanol. So in the ground state, the molecule is planar with a double bond between the carbon and the oxygen, as we see over here. So we've got the carbon and oxygen doubly bonded. The two hydrogens and the oxygen are all in the same plane with the carbon. Now, we expect two lone pairs on that oxygen atom. A molecular orbital describes the position of an electron within a molecule, just like an atomic orbital describes the position of an electron within the atom. In the molecular orbital diagram for formaldehyde that I've got over here, one of the non-bonding oxygen orbitals is mixed with the three sigma bonding orbitals of all the bonds. And these four orbitals, sigma 1 through sigma 4, are each occupied by a pair of electrons with opposite spin, one spin up and one spin down. So that's m sub s plus a half and one m sub s minus a half. So let's look at the molecular orbital diagram for formaldehyde. You can see here we have the three sigma bonding orbitals plus one non-bonding orbital. So we have sigma 1 here, where there's a lot of electron density in between the oxygen and the carbon. We have sigma 2 over here, with a lot of electron density between the carbon and one of the hydrogens. We've got sigma 3 over here, with, again, a good bit of electron density in between the carbon and a hydrogen. Over here, then we have sigma 4, and this is our non-bonding orbital. Going up from there, we have our pi orbital here. So this is the double bond between carbon and oxygen. Then we have N, this is the non-bonding oxygen orbital. So this one and this one are where we have the oxygen lone pairs. And then up here we have that carbon-oxygen pi anti-bonding orbital. So there is a higher energy pi bonding orbital here, and this pi orbital is made from the p sub y atomic orbitals on the carbon and oxygen atoms. We've got electrons in each of the 5 orbitals discussed to this point, so a sigma 1 through 4 and this pi orbital. Those are all causing the carbon and oxygen atoms to attract one another. Then the highest occupied molecular level, the HOMO, is the non-bonding orbital. That's this one here, which is labeled N for non-bonding. This molecular orbital is mostly that O2px atomic orbital, and that's not a bonding orbital. So electrons in that orbital cause neither a repulsion nor attraction between the carbon and oxygen atoms. And the lowest unoccupied molecular orbital, the LUMO, is that pi antibonding molecular orbital. So that's this molecular orbital up there all the way up at the top. And electrons in that orbital cause that carbon and oxygen atoms, those nuclei, to repel each other, not attract each other. So an electronic transition occurs when an electron in one orbital moves to another orbital. And this transition requires an increase or decrease in energy of the molecule along with the photon absorption or emission. So if you are moving from, let's go back here, if you're moving an electron from a low energy molecular orbital to a higher energy molecular orbital, then you have to put in energy. So that molecule is absorbing a photon. If that electron then transitions back down to the hole that it left, it's losing energy, which means the molecule is losing energy. That energy has to go somewhere. It can be emitted in the form of light. So the lowest possible energy transition for formaldehyde involves an electron moving from the HOMO, that non-bonding N orbital, up to the LUMO, the lowest unoccupied molecular orbital, the antibonding pi orbital. And there are two possible transitions here, resulting in two different excited states. The first is a singlet state, so the spins of the previously paired electrons are opposite as they were prior to the transition from the ground state. So that's represented here, where we've moved this electron now from the n orbital up to the pi star orbital. But note, this electron still has spin up, that electron now has spin down, still has spin down, because if they were paired before, they had to have opposite spins before. That second possible transition is to the triplet state, which is where the spins of the previously paired electrons are parallel. So now, this spin is up, and that spin is still up. So now, with this one, we've flipped the spin on that electron, so we have the singlet state and the triplet state. Now, the lowest energy singlet state and triplet states are called S1 and T1, respectively, for singlet and triplet, and T1 is generally lower in energy than S1 is, the singlet state. For formaldehyde, that N to pi star triplet state transition requires visible light with wavelength of 397 nanometers. Going into the singlet state requires ultraviolet light, so slightly more energy, with a wavelength of 355 nanometers. But if formaldehyde absorbs 397 nanometer light, then it's absorbing in the violet region. It should appear the complement, which is yellow-green. But formaldehyde is in fact colorless. So why? It turns out that the probability of a transition between singlet and triplet states is really quite small. That is, formaldehyde absorbs so little of this 397 nanometer light that human eyes can't detect it unless you have a really large amount of formaldehyde. So remember that in the ground state, formaldehyde is planar. But both the S1 and T1 states are pyramidal. That is, promoting an electron from the non-bonding to the antibonding orbital changes the molecular geometry and lengthens that carbon-oxygen bond, since the bond is becoming weaker. Now, infrared and microwave radiation are too low in energy to promote electrons to higher orbitals, but they can alter the vibrational and rotational states of the molecule. Now, formaldehyde has 4 atoms, each of which can move in 3 dimensions. And thus, the entire molecule can move in 4 times 3, which is 12, ways. So, 3 of these are the translation of the entire molecule along the X, Y, and Z axes. 3 of them are rotation of the entire molecule about the X, Y, and Z axes. And this leaves 6 vibrational states, because 12 total states minus our 3 translational states minus our 3 rotational states gives us 6 vibrations. And here we can see the 6 formaldehyde vibrational modes. So we have our doubly bonded oxygen up at the top, carbon is in the center, and on the bottom we've got our 2 hydrogen atoms. So the labels for the atoms are left off here for simplicity. So we have our symmetric stretch, where the oxygen is moving up and each hydrogen is moving down and out. And then they reverse and they move back in. We've got our asymmetric stretching. We've got our carbon-oxygen double bond stretching. We've got our symmetric stretching, where both the hydrogens are bending. Our symmetric bending, where both our hydrogens are bending together. We've got our asymmetric bending, where they're not bending together. And we've got our out-of-plane bending, where the carbon atom is going backwards into the board and the other 3 are coming out, and then they reverse, the other 3 go back into the board, and the carbon atom comes out. So the spacing between the rotational levels is smaller than the spacing between the vibrational levels, and this means that microwave radiation generally alters the rotational state, whereas IR radiation generally alters the vibrational state. And then again, the visible and ultraviolet alter the electronic state of a molecule. So when a molecule absorbs a photon with enough energy to promote an electron, then the vibrational and rotational transitions often will occur as well. Because unless that photon has exactly the right energy, only enough energy to promote the electron, if it has more energy than that, then it can promote the electron and promote the molecule into an excited vibrational or rotational state along with the excited electronic state. But it is possible for one photon to have exactly the right amount of energy to cause transition from the electronic ground state S0 to S1, and transition from the vibrational ground state S0 to S1, and transition from the rotational ground state S0 to S1. The electronic absorption bands are generally quite broad because many rotational and vibrational levels are available at similar energies, just slightly different in energy because the rotational levels are really close together, the vibrational levels are a little bit farther apart, the electronic transitions are generally really far apart. So let's examine what happens to the energy contained in a photon after that photon is absorbed by a molecule. So suppose that a molecule is initially in electronic ground state S0, and suppose further that the absorption of a photon promotes that molecule to a vibrationally and rotationally excited level of the excited electronic state S1. So we're exciting the molecule electronically, vibrationally, and rotationally. So this is then transition A, the absorption process. That's where we're going from the ground state, which is down here, this solid black line, where that molecule is absorbing energy to go up into the singlet state, that S1 state, and it's somewhere up in here where we have the excited vibrational and rotational levels going up from that excited electronic level. So these all have the electron in the same orbital, but the vibrational and rotational modes may be excited as well. Right, so the first thing that usually happens at that point is then a vibrational relaxation down to the lowest level. So we go from here down to there along this R1 transition. Now R1, it's called R because it's radiationless, because we're allowing the energy to go vibrationally to other molecules around. So again, the energy doesn't leave the molecule via a photon, but through collisions with other molecules. So as that molecule collides with other ones, some of that energy gets transferred to the other molecule, and the molecule that we're interested in that has absorbed the photon has lost a little bit of energy. It does this a few times, and it eventually gets down to the lowest vibrational level of our excited electronic state, S1. So the energy is leaving the molecule and spreads through the bulk as heat. So now our molecule is at the lowest level, so now we're at this point of S1, and several things can happen. The molecule can undergo internal conversion, which is IC, that's this one. This process, we can go over here to a vibrationally and perhaps a rotationally excited level of S0, our ground electronic state, but a very highly excited vibrational state. And that's at the same energy here as our vibrational ground state of our excited electronic state, S1. And then from there, then the molecule can undergo relaxation process R2, that vibrational relaxation, again radiationless, to return down to the ground state. And note that this path of absorption, vibrational relaxation, internal conversion, vibrational relaxation, has caused all of the energy from the photon to be transferred into the bulk as heat, because we transfer some of the energy here as heat, and we transfer the rest of the energy there as heat. But if we go back to our molecule in this state, there in the ground vibrational state of the S1, our excited electronic state, that molecule could undergo instead intersystem crossing, or ISC, to go over here into the triplet state. And again, it's going into a vibrationally excited state, and then this can be followed by a vibrational relaxation. So that's this one, down. This is R3, vibrational relaxation 3. And then, now that our molecule is at this point, we can have one of two things occur. Either an intersystem crossing can go back to our electronic ground state, but a highly excited vibrational state within that. That will then be followed by R4, the vibrational relaxation of that energy back down, of that molecule back down to the ground state. And again, in this case, we've had some absorption by the photon, relaxation so that energy goes out into the bulk as heat, intersystem crossing to the triplet state, back down, some energy has gone out as heat, then an intersystem crossing back to the singlet, now the S0 state, and then vibrational relaxation that heat goes out into the bulk again. So again, in this case, all of that energy has gone out into the bulk as heat. But let's go back to our molecule in this state, back in our triplet state. Instead of undergoing intersystem crossing back to the ground electronic state, our molecule could emit a photon instead. And if it emits a photon, now this process, that's called phosphorescence. Because now we have our molecule returning from its triplet state to the singlet state, singlet ground state. That triplet to singlet transition emitting a photon is called phosphorescence. But now let's go back even farther and to our molecule that was over here. We said it could go this way through internal conversion and lose its heat, lose energy as heat that way. We said it could undergo an intersystem crossing over here to the triplet state. But from that state, there's also a possibility that it emits a photon directly from that excited singlet state through this process called fluorescence. So again, it's emitting a photon just as it did over here in the phosphorescence. So note here that fluorescence is a transition between singlet states. We're going from singlet 1 to singlet 0, the ground state, while phosphorescence is a transition from the triplet state to the singlet state, back to the ground state. Furthermore, the phosphorescence necessarily involves a smaller amount of energy than the fluorescence does, and this means that the fluorescence occurs at shorter wavelengths, the phosphorescence occurs at longer wavelengths. So also note that the rates or the probabilities of internal conversion, intersystem crossing, fluorescence, and phosphorescence depend upon the molecule. So some molecules have particularly high or low rates of each one of these. And fluorescence and phosphorescence are generally relatively rare. Most excited state molecules will decay back to the ground state via radiationless transitions. So they'll lose their energy as heat, in other words. So the lifetime of fluorescence is about 10 to the minus 8 to 10 to the minus 4 seconds. The lifetime of phosphorescence is significantly longer at around 10 to the minus 4 to 10 to the plus 2 seconds. And this is because phosphorescence requires a change in magnetic spin quantum number, that m sub s value, which is an improbable transition. So it takes a lot longer for us to get our molecules out of this state and back into the ground state. So there are a few known materials like europium and dysprosium-doped strontium aluminate that phosphoresce for hours after exposure to light. And these are generally the glow-in-the-dark objects that you're probably familiar with, stars and toys and things like that. So that was what happens when a molecule absorbs light.